The first point to make is that when you're finding a general solution of a scalar equation like this, you do not need to convert to vector form. Again, we're guessing solutions of the form e to the st, where s is an unspecified and unknown constant that we need to solve for. It's a good guess because we know exponential functions are often solutions of linear equations. So we go ahead and guess it and hope it works. Find the derivatives, plug those in. In this case, you get s squared e to the st, that's the second derivative, plus 6 times s e to the st, that's 6 times the first derivative, plus 8 e to the st, that's 8 times the function. What I'm wondering is, are there any values of s that make this always 0, no matter what t is? It's important to realize that's what you're doing. You want such a function to be in the kernel of this linear transformation, really. This linear operator is a linear transformation. Are there any values of s that work? You should understand the logic here. You factor out n e to the st like this. E to a power is never ever 0. So because of that, that means it's good enough to solve where this quadratic equals 0, which can be done either with the quadratic formula or by factoring. And in this case, you get two roots, -2 and -4. Are those eigenvalues? You could call them eigenvalues. They do end up being the eigenvalues of the corresponding matrix when you convert to a system. And we could call them lambda instead of s if we wanted to. People don't always call them eigenvalues, but effectively they are. So e to the -2t and e to the -4t are both solutions of this differential equation. The differential equation, being second order, has a two-dimensional kernel. This homogeneous equation, thinking of this as a linear transformation, it's got a two-dimensional kernel because it's a second order linear differential operator. And therefore, if you've got two functions that are not scalar multiples of each other and are both solutions, they will be a basis for the solution space. You didn't have to write this, but I could say B equals the collection of these two functions is a basis of the solution space. I mean, that takes proof. The main thing to prove is that the solution space of this, the kernel of the linear transformation, is a two-dimensional vector space. That's some theory that we never really do. But if you trust that, then two linearly independent functions by the basis theorem will automatically be a basis. The vector space here is a collection of functions. And this then justifies the general solution being an arbitrary linear combination of those two functions, say y equals k1 e to the -2t plus k2 e to the -4t, though of course if you wrote those in the other order, e to the -4t there and e to the -2t there, it's equivalent. You can use this to solve initial value problems, though initial value problems for second order equations need two initial conditions. And if this y is position, you need an initial position, y of 0 equals something, and you also need an initial velocity, y prime of 0 equals something, to solve for k1 and k2. Graphs of such functions do not oscillate, right? There's no cosines and sines in there. They decay to 0 without oscillation. Typical kinds of graphs will look like this, or maybe this. In other words, the damping, B, is relatively large. That's overdamped because there's no oscillations. There's so much damping that it makes the position decay to 0 without oscillating. Overdamped. On the other hand, in the other case where B is 4, that's less damping. And it does turn out to be an underdamped case. So now our differential equation is y double prime plus 4y prime plus 8y equals 0. The B is 4 now. Guessing e to the st, like we did before, results in something similar to what you see here, except that 6 will be a 4, resulting in the same kind of thing as you got here, except the 6 is a 4. S squared plus 4s plus 8. And if you haven't noticed already, the coefficients of the second order differential equation become the coefficients of the quadratic function. Roots of that, though, are complex numbers. We need the quadratic formula. -4 plus or minus square root of 4 squared is 16. Minus 4 times 1 times 8 is minus 32. Over 2 times 1, this becomes -2 plus or minus 1/2 square root of -16. Replace square root of -16 with 4i. Multiply by 1/2. Your roots are -2 plus or minus 2i. And yes, you could call those eigenvalues of the corresponding linear system, the matrix for that. You should get the same answer if you did that. As far as finding a general solution, though, we only need to use one of them. Just like in the vector case, you only need to use one of these and Euler's formula to find a general solution. A complex solution, I could call it YC, is e to the, in parentheses, -2 plus 2i times t. That's not the solution we're after. We don't want a complex solution. It's just a tool to help us find the real solution. And I don't need to write this, multiply this times a vector, because I'm just thinking about the scalar solutions. First, do this. That's a property of exponents. Then use Euler's formula. E to the I times 2t is cos 2t plus I sine 2t. What's the reason for that again? If you want to go in depth, it's related to Taylor series. You can derive it using Taylor series. May not be super satisfying for everybody, but that is possible. Go ahead and multiply the e to the -2t through the parentheses. E to the -2t times cos 2t plus I times e to the -2t sine 2t. We could call this y sub re. Notice I'm using a lowercase y because it's a scalar instead of a vector. And we could call this part next to the I, y sub im. Those two real functions turn out to both solve this equation. You can double check it by differentiating and plugging them in. That's not, we didn't derive them that way. We were thinking about solutions being in this form. But it's almost like magic. It turns out they do still work. You can double check it. And they're not scalar multiples of each other. It's a second order equation. The solution space is two-dimensional. Any two linearly independent solutions will automatically span. They'll automatically be a basis by the basis theorem. And your general solution will be an arbitrary linear combination of them. Don't include the I anymore. Just take K1 times the first function plus K2 times the second function. There's a real general solution. That's what we're after. Yeah, you don't have to convert to vector form. You can, but you don't have to. Got cosines and sines in there. Oscillation. There's not enough damping to prevent that. That's underdamped. When you have complex number eigenvalues, it's going to be underdamped. When it's real eigenvalues, and if they're distinct real eigenvalues, it's going to be overdamped. The boundary between the two cases is called critically damped. You have only one real eigenvalue in that case. The characteristic polynomial has a double root. And to find that, essentially you can think about the original equation and think about the corresponding quadratic equation in general that you're trying to solve for S, and think about the quadratic formula and get these roots in terms of B. And the boundary is going to, between real roots and complex roots, is going to occur where this is 0. So B squared minus 32 is 0, will help us find the bifurcation value. It's equivalent to B squared equals 32. So B is plus or minus square root of 32. Well, damping has to be positive, so we could assume B is positive and just take the plus square root. If you allowed B to be negative, then you could also take the minus square root. But B is positive, really. It's damping. So we take the plus square root of 32, which is the same as 4 square root of 2, right? Because 4 squared is 16, and 16 times 2 is 32. Should be between 4 and 6. Yeah, it will be. About 5.66 is your bifurcation value. How do you think about this in terms of real life? You might wonder, does anybody ever observe the critically damped case? Guess what? No. It's impossible to actually in the lab observe a critically damped case. I would be shocked if there ever was one in the history of the world. Why? Because it's just one precise value of B as a real number that would have infinitely many decimal places of precision. Nobody's ever going to come up with an experimental setup having that kind of precision. So in the lab, you would only observe overdamped or underdamped. You would never observe critically damped. So why do we care about critically damped? Well, mathematically, it's still the boundary between the two.
What would the critically damped graph look like?
It doesn't look much different than overdamped. In terms of phase planes and corresponding linear systems, let's think about the corresponding linear system here. So here again is our second order equation with prime notation. Prime notation to save time. The corresponding linear system has a first equation that essentially defines the velocity, and a second equation for the derivative of the velocity found by subtracting 8y and bv from both sides. Negative 8y minus bv. If the y equation is first and the v equation is second, it's best to put the y term first and the v term second so that you get the right matrix. The matrix would be of a first row of 0, 1 and the second row of negative 8, negative b. If you did these the other order, you'd mistakenly write negative b, negative 8, but that would be wrong. The trace of a matrix, if you're up on your reading and lecture watching, is the sum of the numbers in the main diagonal. That's called the trace of a square matrix. The sum of the numbers in the main diagonal, 0 plus negative b in this case, which is negative b. It's called the trace. And the determinant, as always, is a times b. In general, it's AD minus BC. In this case, that simplifies to 0 minus 1 times negative 8 is positive 8. The characteristic polynomial turns out to equal lambda squared minus the trace times lambda plus the determinant. Set that equal to 0 to find the eigenvalues. It's minus the trace, not plus the trace. You get lambda squared something's wrong. Okay, no. Lambda, the trace is negative b, so minus the trace times lambda is actually plus b lambda plus 8. Well, we already knew that. So that's a lot of work to confirm what we already knew, right? The coefficients are 1, b, and 8, just like up here. But it's good to see that it works out. And just like before, you can use the quadratic formula to find the bifurcation values, or more generally in section 3.7, or is it 3.8? I'm forgetting. You want to use something called the trace determinant plane. This trace determinant plane, TD plane, touchdown, will help in other situations besides this kind of situation. We don't need it to find the bifurcation value for this situation. But there's other situations where you don't necessarily have a harmonic oscillator. You just have a linear system that depends on a parameter, where this trace determinant plane is definitely very helpful. This trace determinant plane, you want in it, you want to mark off 3 special curves. They're called critical loci. Loci is plural of locus. Locus means curve, essentially. One of them is the t-axis. Make it darker. One of them is another one is the positive d-axis. Make that darker, not the negative d-axis. And another one is a parabola whose graph looks about like this. Its name is called the repeated root parabola. Its equation is d equals t squared over 4. It's a quadratic function of t. It is a parabola. It's sometimes nicer to think of that without a fraction, to write it as 4d equals t squared. And how do you use this trace determinant plane? You've got either, well, in general, you've got a matrix that depends on a parameter. In this case, capital A depends on B. That's a B, not a 6 there. Negative B. And the trace and determinant depend on B in general as well. What you want to do is you want to take those dependencies and treat this set of equations like a parametric curve, where the parameter is B, not time t, but B. Let's write it down here. T comma D equals negative B comma 8. As B varies, this traces out a curve in the plane. Very simple curve in this case, a line, a horizontal line. Because D is the second coordinate, 8, it's constant. First coordinate's negative B. If B starts out at a value of 0, when B is 0, you're on the positive D axis at 8. And then as B increases, the T coordinate here decreases. The point moves to the left. Anytime, here's the punchline. Anytime one of this curve here, this TD curve, as a parametric curve in the parameter B, touches one of these critical loci, you could argue a bifurcation occurs. One place it touches is right there. How do you find the corresponding value of B? Take these things and plug them in that equation, there and there. 4D equals 4 times 8 is 32. Equals t squared, that's negative b squared. The negative sign goes away. You can write that as b squared. B squared equals 32. Oh, we saw that equation 10 minutes ago. Therefore, b equals square root of 32. Just like before. 4 square root of 2. That's the bifurcation value. Could you argue that this point corresponds to a bifurcation value? You could actually. B equals 0, the starting value of B, when there's no damping. Actually, I wrote B as positive there, not equal to 0. I could include 0. If B equals 0, then there's no damping. Harmonic oscillator that never decays in amplitude. No exponential decay to the general solution. You'd only have cosines and sines. The eigenvalues are purely imaginary numbers in that case. That's called undamped. Un as in no damping. You'd be right here if that were the case. Now, if you allowed negative B's, maybe because you didn't care about harmonic oscillators, but you just like thinking about differential equations, then your curve would start back over here and still be heading to the left as B increases. In terms of the phase plane, it's important to know that when the TD coordinates are in this region here, that the origin is a spiral sink in this region here, above the repeated root parabola where t is negative. That corresponds to a spiral sink, eigenvalues that are complex and have negative real part, just like happened here. Spiral sink. If you convert it to vector form and draw solutions in the phase plane, it'll look like that. When you're over here, it's a real sink, or you could just call it a sink for short. You're going to get real eigenvalues and real eigenvectors. You'll get straight line solutions. And I think typically it looks about like this. And other solutions curve in. At the boundary, that's the critical locus where it's a repeated root parabola. There's only one eigenvalue that's repeated, critically damped. It doesn't look too much different from this, although there's only one line of straight line solutions instead of two. I won't bother drawing. If we allowed negative values of B, and we're over in here, the origin would actually be a spiral source. I guess instead of damping, you'd call that anti-damping. Or maybe amplification. That would be a better word. Maybe if B is negative, that corresponds to a circuit you could make where there's an amplifier. I don't know, just guessing, maybe. Spiral source, when you're over here, it's a real source. Two straight line solutions, and solutions move away. Maybe something like that. For this particular system, you're never down here. The determinant is never negative. You look at this matrix, its determinant's always 8, no matter what B is. Never negative. So you're never down here, but what happens in general if D happens to be negative? Down here, it's corresponds to saddle points. One eigenvalue is going to be positive, one's going to be negative. That doesn't happen with harmonic oscillators. But it could happen in general for linear systems. Whenever the determinant is negative, you have a saddle point. This is the repeated root parabola. That's where one eigenvalue that's repeated. The positive d-axis is where you have purely imaginary eigenvalues. Down here, you've got one positive eigenvalue, one negative eigenvalue. What about the t-axis? What happens there when d is 0? That's called the degenerate case. And lots of weird things can happen then. Like you can even have infinitely many equilibrium points. That's the typical thing that happens actually, if the determinant is 0. That should make sense. If the determinant of a square matrix is 0, then it's a linear transformation. It's not 1-to-1 and not onto. Its kernel is going to be non-trivial. The kernel would correspond to the equilibrium points. There'd be infinitely many of them. All this stuff fits together. Hanging with me here? Can I clarify anything? Again, this is just a tool. This trace determinant plane is just a tool. That's not a solution curve. It's just a tool to help us think about how the trace and determinant vary as the parameter changes. That's all it is. But it's kind of a fun tool, I think. And it can be more complicated than this. You could have a curve that goes all over the place. And you could have lots of bifurcation values.